We're back. We're back to the wonderful world of transformations, and we're going to look at some horizontal stretching of functions today. So a little bit difficult, a little bit more difficult, I would say, from what we have done in the past, but still doable. And we're still going to practice these. So here we go. Here is our note sheet that we're working with today. And up at the top, it does say perhaps one of the hardest transformations of functions occurs when we horizontally stretch. So please understand, I know that this is challenging, okay? And it says these types of transformations can be vital, especially when we model a process over time, when we shrink the time interval. So these are more challenging just from a visual standpoint. I think they look backwards from what we would expect. Normally our horizontal transformations will look backwards. Okay, so we're going to consider the absolute value function of x, absolute value of x minus 2 and then minus 3. So it says using our calculator, we're going to sketch a graph of f on the axes provided and then label the coordinates of its vertex point without the use of your calculator. Okay, so I use Desmos again, because that's where we're at these days. And just so we understand how Desmos works, at the bottom over here, you have this little keyboard. And if you open it up, here's where you get that absolute value function. So if you have the absolute value, I've already typed it in, of x minus 2, and then arrow over so you can do minus 3, that gets you this function. All right, so that would be the graph, and it wanted us to find its vertex without the use of our calculator. Well, here's what I'm going to do. I'm actually going to go back and say, just so we have an idea of the absolute value of x, what does that look like? Let's graph that. Okay, so if I'm thinking from our last unit, maybe what's going to be going on here? Well, I definitely know it's got to be going down 2. And because this is with the x, we know we should be shifting it, looks backwards, right 2. Okay, so checking this out, actually, think about what we just said. I should be going to the right, and then I should be going down 1, 2, 3, and there we go. So that vertex should be at 2, -3. Okay. Oops. Let's do this. So our vertex is at 2, -3. And now I know I used the graph to kind of help out, but this is all based on transformations. So again, this is saying shift down 3, and this 2 is saying go to the right 2 units. So that's how we came up with that vertex. Okay, so now we're going to consider the function g of x, which is f of 2x. Now think about that, f of 2x, different from our last one when we did the vertical stuff, where the 2 would have been on the outside. Okay, so this looks a little bit different. It says determine a formula for g, and then graph it on the axes, and use your calculator to find its minimum point. Okay, so if we were to take the graph that we have up above, which is g of x, and we now need to say that it is going to be anywhere I see an x, I'm going to make it a 2. So in my function, my absolute value function, there's an x now. I'm going to make it a 2x. I still have the minus 2 and then minus 3. Okay, so a couple of things that we could do here before we grab our calculator or we go to Desmos is, in this function, I could factor out a 2. And then I would get the function x minus 1 minus 3. Okay, so if I'm looking at that, that's almost looking kind of like our original one. So it's looking like it's shifting it down 3. Maybe it's looking like it's going to the right 1 unit. Okay, from that part inside the parentheses, and then we have that 2 on the outside. All right, so let's take a look. If I go and we graph this out, just to get some ideas in our head, sometimes it's nice to look at the functions and think about them first. So we're going to graph out the absolute value, and you could write it in either form that we had. So we had 2. I'm going to put it in the other form that we factored out that 2. So I'm going to have x minus 1, arrow over. Okay, and then arrow over one more time, so we're out of the absolute value, and then I can say minus 3. I press enter. Notice what we got. So that blue graph, that's the one that we're just taking a look at right here. Okay. And the minimum point, again, I'm going to make my keyboard a little bit smaller. That minimum point, if I just click on it with my mouse, I can find that minimum point at 1, -3. Isn't that interesting that we kind of had that over here? Okay. So that minimum value is at 1, -3. Okay. We're going to do another one. So now we're going to consider the function h of x. And again, it's taking our function, and anywhere I see an x, I'm making it 1/2 x. Okay, so h of x. Here we go. So in the original function, anywhere I see an x, which is right here, I make it 1/2 x. And then I have -2, and then -3. Okay, and then we need to find its minimum point. So I'm going to try and do what we did up above. And I'm going to factor out the 1/2. So now we have to be careful. It's kind of weird factoring out a 1/2. No big deal here. That's that's x. Now I have to think 1/2 times what would get me 2? Well, 1/2 times, how about 4 would get me 2. And don't forget it's negative, so we got to keep that sign there. Okay, and then -3. So using what we did up above, that would make me think our minimum value should be at the location for -3. So let's see what we have when we go to Desmos. We're going to go type in here. Again, I'm going to get my absolute value. And I'm going to type in, again, the same thing that we kind of had factored out. So I have 1/2 and then parentheses, and we have x minus 4. I'm going to shift out of those parentheses the absolute value and do -3. If I press enter, we have our graph. And so now that's saying that's the green graph. And now let's take a look over here. Notice your vertex. Okay. And if you want to check, if you're like, wow, this woman's just making stuff up, what if I plugged in that other function? Okay. So what if we did 1/2 x minus 2 minus 3? Notice what happens. We get that same graph right there. Okay. So just so that you can see, these are both the same functions. They both have that same minimum value of 4, -3. Okay, so it's to summarize your findings below for each of the functions. So we know the turning point for our original one, we said, was at the location 2, -3. And then the turning point for the second one we did was at the location 1, -3. And then the last one that we did was at the location 4, -3. Okay, so let's notice what stayed constant so that maybe we can find some patterns here. So things that stayed constant. All right, well, it looks like our y value. Right, y value didn't change. There should be an apostrophe in the didn't. And y value didn't change. That was constant. Okay, so what did change? Well, the thing that did change was our x values. Okay, so something that you might want to think, and this is just the way my brain works, maybe you have a different way to think. I always think it's opposite. It's opposite of what I want it to be. Okay, so if I were to multiply by 2, notice what really happened. So like that second example we had, the f of 2x, when I multiplied it by 2, it really divided by 2. Okay. And in that next one that we had, that part C, that f of 1/2 x, when we multiplied by 1/2, all right, that really divided by 1/2. Okay. So keep it in mind. Horizontal motions, they look a little weird, but we almost want to think opposite, kind of like what we've been doing before. And our horizontal motions, just like if you think x-axis is horizontal, should only be affecting your x coordinates. Okay, so horizontal dilations, all right, that's what we just did. And it says the function f of k of x, it represents a horizontal compression, or sometimes you'll hear it say like a shrink, and it says by a factor of k. And then the function 1 over k represents a horizontal stretch. So you would think big, right? You'd think big number, and we have this 1 over k, which is a fraction. So that's where that opposite kind of comes in. Same thing back up here. If I have a big number, a whole number, I would kind of think this would be, if this is a big number, I would want to think stretch, but notice what it does, it compresses. So that's why I'm kind of saying it's opposite. Small little fractional value is a stretch, big number is a compression, think opposite. Okay, so we have number 2. We're going to take a look at the quadratic function, and we're going to determine the coordinates of its turning point by using the equation for the axis of symmetry. So we've done this in our past, and so we know it's going to be x equals negative b over 2a. So when we look at the equation, our b value is negative 12. So we have x equals a negative 12 all over 2 times 1. And if we simplify, so our x value here is 6. Okay, so we want to determine the coordinates of its turning point. So I have x, that means I need y. So now we're going to go back in, we're going to plug in 6 into our function. So I have 6 squared minus 12 times 6 plus 20. And if we simplify that down, that's going to get us a value of negative 16. So that gives us a coordinate of 6 comma negative 16. So if G is defined by f of 3x, what should the coordinates of its turning point be based on the previous work? Okay, so first I'm thinking, okay, that looks like a big number. I would want to think stretch, but it's not. It's going to shrink it. It's going to be a compression. Okay, and I also want to think it looks big, but I want to take the reciprocal when I'm multiplying this out. Okay, so if I know that my turning point was 6 negative 16. And I also know, because it's a horizontal motion, horizontal axis is your x-axis, it's only going to affect my x coordinate. I have 1/3 times 6, and then nothing happens to the 16. That's going to stay 16. That's your y coordinate. Okay? So if I take 1/3 of 16 now, or I'm sorry, 1/3 of 6, I get 2 negative 16. Okay, so that's the coordinates of the turning point. Based on our work, I know it's going to be a transformation that's going to be kind of opposite of what I'm thinking. So I need to think multiply by the reciprocal. So that might be something you want to tell yourself, multiply by the reciprocal. In fact, I'm going to type that down so that we don't forget this. Multiply by the reciprocal. Okay. So now we're going to determine a formula for g of x, and then we're going to use the turning point formula to verify our answer from part B. All right, so if we need to find a formula for g of x, keep in mind what they've told us back here. They told us it's equal to f of 3x. So I'm going to go and find g of x and say, okay, g of x is going to be the f of 3x. That means in my f function, anywhere I see an x, I'm going to replace the x with 3x. Okay, so I have 3x squared. Anywhere I see an x, I'm going to make it a 3x plus 20. And now we're going to simplify. Okay, so 3x squared, remember you have to square both the 3 and the x, so now you have 9x squared minus, now I have 12 times 3, so 12 times 3 is 36x, and now I have plus 20. So now this is our new g of x. That formula is what we have. And now what it wants us to do is verify our turning point from our answer. So again, we have to go back and use that x equals negative b over 2a formula. So I have a negative 36 all over 2 times a. So a negative 36, we get a positive 36 over 2 times 9, which is 18. So I have 36 over 18. And when we simplify that down, that's going to get us 2. So I know our x value here is 2. So far, so good, because that's what we got back there. And now we need to find our y value. So our y value, we'd have to take that value and plug it back into our formula. Okay, so I would have 9 times 2 squared minus 36 times 2 plus 20. And when you simplify that down, lo and behold, you get a negative 16. Okay, so again, we do get that coordinate like we kind of predicted up above, just using our transformation rules of 2, negative 16. Okay, so now we need to show that the y-intercept of both f of x, the original function, and our transformed functions are equal. Okay, so if it's a y-intercept, that means x is 0. So in my f function, anywhere I see an x, I'm going to make it a 0. Okay, so back up above, remember what our expression was, x squared. So I have 0 squared minus 12 times 0 plus 20. Okay, simplifying that down, we get 20 for a y-intercept. That should be a 0. Okay, and now we're going to do it again for g of x. So g of 0. And so again, I'm plugging it into our formula that we found in part C. So I have 9 times 0 squared minus 36 times 0 plus 20. So I have 0 minus 0 plus 20. So again, now I have g of 0 is equal to 20. So they are in fact equal, right? So I got 20 for both of them. It says, why does this make sense from a horizontal dilation perspective? Okay, so if I'm thinking about this, if I have my x values and I would want to dilate them, my x values for the y-intercept are both going to be 0, right? So if I'm thinking this is 0, 20, this is 0, 20. And if I were to try and change this according to the transformation that we had back up above, I should be taking that 0 and multiplying it by 1/3 or dividing it by 3. 0 divided by 3 is 0. It's not going to change. Okay, so your x coordinates aren't going to be affected. All right, so let's go to our next exercise that we have here. And on number 3, it says, consider the function f of x, and it's graphed on the grid below. G of x is our new graph that we're going to make, which is our current graph, but 1/2 x for all values of x. Okay, so if we were, again, we did this on our last worksheet, if we were to kind of take a look at the coordinates that we have, our coordinate that we have here is -3, 4. And the coordinate below it, we're going to have a value of -1, -2. And to the right of that, we have a coordinate of 3, -2. And above that, we have a coordinate of 4, 3. So those are the coordinates that we are working with here. Okay. So it's asking us, it says evaluate each of the following using the definition of G, and then state the point that lies on its graph as a consequence. All right, so if I were to find G of -6, so using this definition back here, that means I should have the f of 1/2 times -6. So in other words, I should have the f of 3. Okay, well, in order to do this, what we probably need to do is actually figure out what these new points should be. Because notice what I need. What it's saying here is I need to know, well, what's our new function? The function evaluated at 3. All right, so let's go back and let's do this for all of these coordinates that we found. All right, so if I go back to, let's say this first one here, -3, 4. And I want to find my new coordinate. Remember what we're going to do. We're going to take the reciprocal and multiply the reciprocal by the x value. So the reciprocal of 1/2 is 2. So I'm taking -3 and I'm multiplying it by 2, comma 4. So that means my new location here for this coordinate should be -6, 4. So I'm going to graph this out. So I'm going to have -6, +4. That's my new location. Okay, let's go back and try the next one. So I have a -1, comma -2. So again, I have to take my value, multiply it by the reciprocal. So the reciprocal of 1/2 is 2. The y stays the same. So -1/2 times 2, I get -2, comma -2. Okay, so if we go and graph that, so -2, -2, notice what's happening. Notice how it's horizontally stretching it. Okay, if we go back, I go to my next one. So the next one we have is 3, -2. But again, I'm changing the x values, and I'm going to have the x value times 1/2, and the y value stays. Okay, so 1/2 of 3, you're going to get, or I'm sorry, I did that wrong. Whoops, daisies. I want the reciprocal. I did not do the reciprocal. Reciprocal. Okay, so we're going to have the reciprocal. 2 times 3, that's going to get us 6, comma -2. So if we go over again, we're going to graph 6, -2, again, horizontally stretching it. And now our last one we have is 4, 3. Again, multiply it by its reciprocal. So the reciprocal of 1/2, you got 2 times your x coordinate, y stays. So that's going to get us 8, 3. Over 8, and I'm going to go up 3. It's going to be our new point. So if I connect them again, remember what's going on. We are horizontally stretching this. So it definitely got bigger from that horizontal perspective. And we would say it's getting bigger by a reciprocal, right? So think multiplying it by 2, we can see how it expanded out. Okay, so now that we have our graph, now let's go back and see if we can answer this question. So I needed here the f of -3. So our f function is our blue function. So if I go to the f of -3, I should be able to find what my y value is. And then 1 second here. Okay, so if we're taking a look at this, the f of -3, we already can see up here on this graph should be 4. So I know f of -3 is 4. So what does that give us? That gives us a new coordinate that says, if we put this all together, -6, comma 4. And notice what we had back up here. We had that answer -6, comma 4. Let's try another one. So we have the g of -2. So in order to figure out what the g of -2 is, let's try the function notation first, which says I should take the f of 1/2 times that -2. Okay, so the f of -1. And if I look on our graph, the f of -1 should give us 2. I'm sorry, -2. Okay, and if we look at the graph that we're looking at is the black graph. So if I go f of -1, that gives us that coordinate right there at -2. So what does that mean? If we put this all together, I now have the coordinate -2, -2. Okay, so let's try it again. G of 6. So in order to find the g function, g of 6, okay, and notice again, we already have this answer. We have this answer back here because we did the calculations already. All right, the g of 6 means I should be able to say, according to the f function, it should be the f of 1/2 times 6. Okay, so the f of 1/2 of 6 is going to get you 3. All right, and again, go to your black graph. So the f of 3, so I'm reading over 3 on the x, I read down 2. So I have a -2. And so again, if I put this together in the g function, when x is 6, The y value is -2. I would try the last one. G of 8. So again, calculation wise, I should be doing 1/2 times 8. So that's saying I should be finding the f of 4. As I read over 4 up 3. So I know the f of 4 gets me 3. So that means in my new function, my g function, when x is 8, y is 3. Okay. So it says graph G on the grid to the right. We actually already did that. We kind of did that backwards. And then how would you describe it? Well, if I'm looking at this, I'm looking at it as being horizontally stretched, and we kind of already said that. So I would say it's horizontally stretched by a factor of 2. Okay. Again, this is tough stuff. Completely understand. Have no fear. We're going to go over it in class. And if you have any questions, please let me know. We'll practice this quite a bit. Okay. Hope you guys are having a great day, and we'll see you later.